All right, so today we're continuing our section on applications of the derivative. This time we're going to be talking about related rates. So rates are are very closely related to what we've been doing so far. Remember that derivative, we sort of called it a general form of our slope. And slope, if you really boil it down, was just a rate of change. That is, one value is changing in respect to another value. So it's of interest for us to look at rates in terms of applications. And, well, as you can probably tell from the name, how are these rates related to each other? All right, so let's go ahead and start us off. Let's recall some notation about the derivative. So here I have dy dx. What does dy dx stand for, more or less? Yeah, it is the derivative of y in respect to x. In other words, we know that y depends on x, and we're taking the derivative of y. So we said the derivative of y with respect to x. So if I look at dy dt, we sort of touched on this a little bit last time. What does dy dt stand for if I'm just comparing it one to one? Yeah, the derivative of y with respect to t. So the derivative of y. And what parameter do we often use for t? What does t usually represent? Yeah, time. So dy dt is the derivative of y in respect to time. And again, we've done this a little bit already with our velocity, acceleration, and position. Those are functions that depended on time. So whenever I took the derivative, we're taking the derivative in respect to time. All right, so we have this notation dy dt. And really, I can extend this to any variables depending on what I'm looking at. All right, so using that, what we're going to actually do is jump straight into an example, if I timed this correctly. Perfect. Example 1. Let's say I have a UFO, and what do UFOs do? They like to steal cows and create crop circles. From my own experience of seeing them, of course. And let's say that they create this crop circle and it grows at a constant rate. And let's suppose that somehow we know that the area of that crop circle grows at a constant rate, well, at a rate of 6 meters squared per second. So before I read this question, as you probably expect, I have a little bit of animation here. Here I have a cow. So I have a UFO. It comes, it takes the cow, and it leaves behind a crop circle. So my question is, how fast is the radius changing when the radius is exactly 3 meters? So we have not encountered a problem like this yet so far. The closest thing we've done is an application of position, velocity, and acceleration. So the question is, how do I even deal with this? So let's talk a little bit about this example. I have this here. What are some things that might be useful in this example? Let's start off with, what type of shape am I working with? A circle. I have here that my UFO made a circle. Again, if I time this correctly, there we go, clearing that. We have a circle. What other parameters of a circle are mentioned here? Like things that are interesting about a circle that I might measure. Yeah. Yeah, we talked about area and we talked about radius. So if I think about area of a circle and the radius of a circle, is there really a formula that relates the two parts of a circle, the area and the radius? There definitely is. Anyone remember what that equation is that relates area and radius of a circle? I'll start us off. Area is equal to Yeah, pi r squared. And just so everyone knows, this is how I write my pi's. I don't put the little squiggly line for it. All right, so it was important that I talked about how area and radius is related. So what other pieces of information appear to be used in here? I found out that I was using a circle, and I know I was talking about area and I was talking about radius. What other pieces of information appear to be given here? Yeah, we have a rate of change. What rate of change are we given? Yeah, we have how's the area changing. So if I look at this, it says a rate of 6 meters squared per second. And y'all just told me that is how the area is changing. So I'm going to lead y'all through this first example. That tells me I can go ahead and say that dA dt is 6 meters squared per second. Again, remember what dA dt means. This is how is my area changing over time. In other words, that is the rate of change of area. What other information appears to be given here in any of this paragraph that I've put on the board? It's a constant rate of change. And fortunately, we have that already down here. This is our rate of change, and we're saying it's a constant 6. What about in our question? Yeah, we're going to look at the moment when the radius is 3 meters. I'm just going to write that down. We're looking at when radius is 3 meters. That was using this. One big question is, what am I even trying to solve for variable-wise? Well, I'm saying, how fast is the radius changing? In other words, I'm asking, not really a trick question. Well, it might be depending on how you're thinking about how I'm saying it. But if I'm saying, how fast is the radius changing? A way that I could reword this is, what is the rate of change of the radius? So if I'm asking, how fast is the radius changing? That is me also asking, what is the rate of change of the radius? The rate of change of the radius, that is, what is dr dt? So whenever I'm asking how fast something is changing, I'm asking, bless you, I'm asking what is the rate? Or in other words, what is that derivative value? So I claim that this is pretty much most of the information I can really pull from this paragraph. I have an equation, I have dA dt, I have dr dt, and I have r. Right now in this equation, I'm not seeing a dA dt, I'm not seeing a dr dt. How could I possibly manipulate this or adjust it so that it involves these two rates of change? So in other words, what can I do with this? Well, what is dA dt? We're not even talking about the application or the context of the problem. If I told you what is dy dx, you tell me that's a derivative of y, right? Well, dA dt, that's just saying the derivative of area. So the derivative of a in respect to time, that would just be 1 dA dt. What is the derivative of the right side of that equation? I'm going to do a recap after this. What is the derivative of pi r squared? Yeah, I heard someone say 2 pi r. And I'm also going to throw on a dr dt. What I did here was we basically just did implicit differentiation in respect to time. Remember how before we said derivative of y? Anytime we took a derivative of y, I had to write dy dx. And we didn't do it for a derivative of x, otherwise we thought that you would get dx over dx. Here, since I'm taking the derivative in respect to time, I have to throw on the d whatever dt's each time I take the derivative. All right, so before I move further, any questions about how I got this new equation? This is the derivative equation of the original. Yes, technically. Power rule because we brought down to 2. Chain rule because we're not doing the derivative of time. We're doing the derivative of radius, r, in respect to time. So I claim that this is perfect for us to get dr dt. And here's why. What's dA dt again? dA dt? Yeah, dA dt is 6, right? We have that right here. We know what this is. That's 6. This is 2 pi. What's my radius moment that I'm looking at? Yeah, when radius is 3. And then I want dr dt. So I'm going to leave that alone. There's a couple things I haven't mentioned yet that I'm going to try to clarify after we get the solution, by the way. So now I have to go ahead and solve for dr dt. Probably what might be a good idea is let's go ahead and clean this up. We get 6 is equal to 6 pi dr dt. And then I can divide the left and right by 6 pi. Sorry, I'm running out of space here. And I get dr dt is equal to 6 divided by 6 pi. The 6 is canceled out, and I get 1 over pi, for example. So I have the numerical value, but what is the unit of measurement for the rate of change of the radius? We could do some quick dimensional analysis. I could have plugged in 6 meters squared and 3 meters and then checked out where all the meters and seconds went. But I also have a quicker way of doing this. This is how is radius changing over time? What do we measure the radius in? What do I measure time in? So I have meters per second. Because that's what dr dt is for. How is the radius changing over how is the time changing, if I want to think of it that way. So in other words, I have this crop circle that's growing. And the moment the radius of that circle hits 3 meters, I know that the radius was actually growing at a rate of 1 over pi meters per second. One thing I want to note here is notice I did not plug in 3 into this original equation. I plugged it into my derived equation. Because if I plug this 3 into here, all that does is give me the area when we're at 3 meters. That doesn't give me anything about the rate of change or anything like that. So I held off from plugging in R since I know that I'm looking for not area, but the rate of change of the radius. I was looking for rates, not these A and R, for example. All right, so we have part A complete. You can now calculate how fast a crop circle is growing radius-wise. Any questions about how I did this part A? All right, so let's look at part B. Part B, I'm going to keep this first paragraph the same. And I don't know why this text decided to get larger. So since I kept this first paragraph the same, I'm still talking about a circle with pi r squared. And I still know that dA dt is 6 meters squared per second. That hasn't changed because that wasn't part of part A. That was part of the original paragraph. But in part B, I'm now asking, how fast is the radius changing when the circumference is 4 meters? And I'm going to put this in the box and just write, this is what we were given already. That's something that I'm keeping consistent through all of these, both parts of this, parts A and B. So in part B, first off, what am I looking for? What variable am I trying to solve for? Am I solving for a rate or am I solving for a regular variable? Yeah, we're trying to solve for a rate because I'm asking how fast. So in particular, how fast is the radius changing? So I know it's going to be d something dt. In particular, what rate am I solving for? D what? dr, the rate of change of the radius. This is what I want when I want to see how fast the radius is changing when my circumference is 4 meters. So let me just go right when capital C is equal to 4 meters. If you want, you can put this in a box and say, this is our scenario that we are given, that we have now. I have my base scenario and then my extra new scenario conditions. All right, so this looks a little bit different than before. If I want, I could still look at that derived equation. We still could look at dA dt is equal to, we said 2 pi dr dt. We still have that from before. That's again just taking the implicit differentiation of the area equation. How is this problem initially different from part A? What was given in part A that's compared to what's given here? Yeah, in this problem, we're given circumference instead of radius. So what I'm going to try to do is there any equation that relates either circumference, area, and or radius? I'm calling back all the way back on y'all's geometry knowledge from way back whenever. Circumference is equal to, so circumference, I'll put this as a side note. We remember that circumference is 2 pi r, or pi times diameter, whichever way you want to put that. So if I have this equation, if I know the circumference, I should know the radius, right? Because right here, if my circumference is 4, I can figure out what a radius is. So here I can solve for radius very quickly. We get r is equal to 4 over 2. We get 2 divided by pi meters, technically. The reason I did that is that here, well, when circumference is, radius is 2 over pi, meaning instead of looking at this, I can just r is 2 over pi meters. Now by looking at this, I have pretty much the exact same problem as before. I want dr dt, I have r, and I have dA dt. So I'm going to plug in all the things I need into this differentiated equation. dA dt, that's 6. 2 pi, that's an r here, 2 pi r dr dt. R is 2 over pi, and we want dr dt. Can someone go ahead and clean all this up for me and give me what is dr dt after you clean all of this up? Yeah, 6 over 4, which we can actually reduce, I believe, into 3 over 2. 6 over 4, 3 over 2, yeah. What's our unit of measurement for this again, by the way? For the rate of change of the radius. Meters per second. Again, we think dr dt. What is r measured in? Meters. What is time measured in? Seconds. So in other words, this one was just a slight difference from what we had before. I do want to answer another question also. Why did I not take the derivative of the circumference equation? Why would that not really help me in this problem? Well, let's see what would happen if I took the derivative of that. Derivative of c on the left, you don't have to write this. On the left, we would get 1 dc dt. On the right, we would get 2 pi dr dt. It's great that we're looking for dr dt, but do I know anything about dc dt? No, I don't. So that's why I'm not actually taking the derivative of the circumference equation. It introduces another rate that I have no idea what's going on with that in this problem. So that's why I was focusing on the derivative of area, because I know what the derivative of area is. I know what the value for dA dt is. All right, so any questions about this example 1? Part A and part B. All right, so let's do a recap on what we just mentioned. Sort of, let's put some steps to this more or less so that we can have it a little bit organized. And you don't necessarily have to do it in these steps as well. What we just did here is we did a related rates problem. We did the rate of the area versus the rate of the radius. And we saw how those two things were related to each other. So if I go back and look at those steps I did for those two problems, the first one was I identified what was given to us. And it was also important that I knew what am I trying to solve for. So in those previous problems, we had that we were really given a circle, area, radius. So we know area equals pi r squared. And then we knew what dA dt was. We also figured out that we were looking at dr dt at a certain moment. Step 2, I spoke a little bit ahead of myself, writing out the equations that relate my variables. So that's why I asked, what variables are we working with? Well, radius and area. We know an equation that relates area and radius. And typically, after I get that equation that related my 2 or 3 variables, depending on what I'm working with, we went ahead and took the derivative in respect to time. Because we wanted to introduce, for example, in that problem, our dA dt, dr dt. After I took the derivative in respect to time, what we did was we plugged in our known values, what were we given, and then solving our rate or value that we wanted. Last thing that we did in that problem was we checked what was our unit of measurement and does our answer make sense? So at example 1, part A and part B, my dr dt was positive. What does that mean in the context of this problem? If dr dt is positive, what's happening with the radius over time? Yeah, it's growing because it's a positive value, the rate's positive, so at that moment it was growing. Does that make sense in the context of my problem? I know that my circle was growing larger. Does it make sense that my radius is growing larger at the same time? So if I have a circle that's getting bigger, is the radius of that circle getting bigger at the same time? Yeah, for sure. Because they're directly related to each other. So these are the 5 general steps. Notice I said general because, again, there are problems that maybe we have some nuance, but overall, this is how we approach a problem. All right, so using this, let's go. Let's see. If it decides to crash, that might be the board saying that's enough for y'all today. Well, that still works. There we go. One of my favorite problems, the piston. Suppose that I have a piston that's seated at the top of a cylindrical chamber where that chamber has a radius of 6 centimeters. And then let's say this piston starts moving into the chamber at a constant speed of 4 centimeters per second. I'm going to ask, what is the rate of change of the volume of the cylinder when the piston is 4 centimeters from the base of the chamber? And to clarify, in the question, when I say what is the rate of change of the volume of the cylinder, I'm not referring to the chamber, the actual metal can itself, but I guess you would say the little air cylinder inside of it, to be exact. What was that? The max volume? Let's see, max volume 4, no. We'll talk about how we approach this step by step. And just so that you can get an image of what I'm thinking about, oops. This piston's going down at a rate of 4 centimeters per second. Imagine that this kept on going down. And it's probably not, it shouldn't really be going up, but I'm just doing this because the animation's looping. But it's going down at this rate of 4 centimeters per second. And again, I'm looking at the height, well, the cylinder that is formed from the bottom of my chamber to the top where it meets this piston right here. So let's try approaching this problem from the aspect of our steps that I mentioned before. So looking at this, what are we given? What is some information I can pull out directly from this problem? Here we have a radius of 6 centimeters. I'm going to write that down. Radius is 6 centimeters. What else can I look at? Yeah, we have a constant speed of 4 centimeters per second. Let me write down 4 centimeters per second. But what variable or what is that equal to? Well, before we get that, so what letter is this equal to? Is it S? Let's first start off with this. Is this a rate or a constant value? I just realized that was a terrible way to word that question. Is this a rate of change or is this like a unit of like, yes, it's a unit of constant speed. And in particular, I want to say what I'm trying to get at is that this is a rate because it's centimeters per second. The question I wanted to ask, I was trying to get to was, what rate is this? Is this the rate of change of the height, the radius, the volume, the area? Is my volume measured in centimeters? So it can't be volume. I'm going to say that it's going to be a rate of change of the height of my cylinder. And let's talk about why. So remember, the cylinder I'm looking at is sort of air pocket in here. As this goes down at a rate of 4 centimeters per second, what is changing as I push this down with that cylinder? The height is changing. So my height is changing as my piston goes further in. And this is why I'm saying that it is the rate of change of my height. But there's one slight extra thing we have to do here. As this piston goes down, is my height increasing or decreasing in my cylinder? It's decreasing. The piston's going down. My air chamber is having a shorter height as I go down. That tells me that this should actually be negative 4 centimeters because the height is getting smaller. It's not growing. So that's me using this 4 centimeters per second. Again, I know that this is for sure not volume because volume would be centimeters cubed per second, for example. All right, so that's some given information. Let's look at what are we trying to look for? In other words, our question. So what am I trying to solve for? Well, in other words, what is my main point of the question? So here I see the keywords. What is the rate of change of the volume? Rate of change, that's a rate. So now I'm looking for some d something dt. Yeah, dv over dt, because it's a rate of change of the volume v. So this is what I'm trying to figure out. When the piston is 4 centimeters from the base of the chamber, what does that mean in terms of my variable or equations? Yeah, when height is 4 centimeters. So this answers my question of what am I given and what am I solving for? Another step of that 5-step plan I had was equation that relates all of these variables, radius, height, and volume of a cylinder. Does anyone happen to know from geometry an equation that relates the volume of a cylinder, the height, and the radius?
Like involving time, it's either like V equals like height times R.
Yeah, so from both of y'all, we know that volume is actually pi r squared times the height, because my base is a circle, pi r squared times the height. That gives me the volume. Similar idea as what we do with a cube. The cube, we have the base, and then we multiply it by the height. All right, so that's really my steps 1, 2, and 3 all put together. So I have R, I have R, I have H, I have dv dt, I have dh dt. So if I follow my steps for my in my 5-step plan, next step is I take that equation and we're going to go ahead and actually take the derivative. So let's see what happens here. Derivative of v in respect to time. Well, we do have to be a little bit careful. First thing on the left, derivative of v, we should write dv dt on the left. I have pi r squared times the height. Do I know anything about taking the derivative of something times something? We have a special rule for that. Yeah, product rule. It's a product. So we need, if I want the derivative of a product, I need the product rule. As a reminder, I can label this as my first, and then this is my second. So product rule states that the derivative of a product is the first. The second, the derivative of height in respect to time is 1 dh dt. So first, the second, plus the second, h, and then the derivative of pi r squared in respect to time, we have 2 pi r dr dt. Just enough space here. So this was my step of the problem, differentiate that equation that related all of my variables. Fourth step said, plug in all of my known values. dv dt, I'm looking for that, so I can leave that alone. That's my end goal. Pi times, do I know my radius? Yeah, my radius is 6. So I have pi times 6 squared. dh dt, we know what that is. That's -4. Plus h, the height, we have that as well, times 2 pi r. R was 6. Do we have r dt? Yeah, we don't have that. It looks like I'm missing that. So it looks like the only thing stopping me from finishing this problem is dr dt. I claim that y'all actually know it in this scenario. So first off, dr dt, that is the rate of change of the radius, correct? That's how is the radius changing in this scenario. Yeah, so you have a point here. As I push this piston down, is my radius really changing? Is my little bottom circle growing larger? No, let's assume that this is all. In other words, my radius is constant. And what's the derivative of a constant? 0. So dr dt is actually, I'm squeezing in here, 0. Because 0 means that it's not changing at all. If I said the rate was 1, that means it's growing at a linear rate of 1 over time. Yes, this whole thing, fortunately, 0 on the right. After the plus sign. Let's see, 36 times -4. Let's see, 36 times -4, that's 30 times 4, 120. 6 times 4, that's 24. 130 plus 24, I get one. Did I do that right? Oh, I think I accidentally carried a 1, or I confused myself. Yeah, 30 times 4, 120. 120 plus 24, yeah, 144. -144 pi. What's the unit of measurement for that, by the way? Let's see.
Oh, no, centimeters cubed.
Correct. Because when I want dV over dt, V, volume, is measured in centimeters cubed. Time, we're measuring, in this case, for seconds. I got my numerical value in my units, and now I just want to make sure does this answer make sense? Does it make sense that I have a negative dV dt value? Well, if dV dt is negative, I'm claiming by my answer that my volume is decreasing in this scenario. So as my piston goes down, does it make sense that my air chamber's volume is getting smaller? Yes, I'm pushing it down quite literally. The cylinder is getting shorter, hence the volume is getting smaller. So this answer, at least sign-wise, should make sense for us. It would be another question if I wanted to say, like, if I wanted to take a step problem, I might say, all right, now calculate the pressure in the air in the chamber at that given moment. Using some chemistry and physics stuff, we could do that if we wanted to, but that's going a bit beyond what I want to cover. But yeah, we have the piston problem.
The rate of change is also happens to equal how much volume is left in the cylinder too, in this situation.
The rate of change of what? There's a lot of rates of change just in here.
The rate of change of the volume equals also the volume that's left in the cylinder, correct?
Not the volume that's left in the cylinder. This is just saying how fast it's decreasing at that moment. We don't know if it's like the piston. Well, we sort of do know in this case, but generally speaking, I wouldn't know if the piston was like, let's say it started off fast and then slowed down. So we don't want to make too many assumptions here.
So the volume is just
144 times pi. In this case, I think that one happens to be a coincidence because I used 4 twice. Maybe I should change one of them to like a 3 and a 7 next time. But yeah, that happens to be a coincidence. Actually, I think I had another student mention that before in the previous semester, and I told myself I was going to change it. Obviously, I did not. All right, so last thing I'll mention here, just again, a preview of what we're going to do next time, tomorrow. Other things that we will be doing is the ladder problem. What happens if you pull the foot of the ladder away from the wall? And then like that. And then we'll do the submarine problem. Let's say you have a ship and a submarine that travels directly underneath it, maintaining its position, but still diving at a 25-degree angle. Something like that. And we're going to do some calculations based off of this scenario. What was that? Yes, it's going quite fast. Well, yes. All right, besides that, that is all for today. I will see you all tomorrow. I don't know why I looked at my wrist like I had a watch, but tomorrow is Wednesday. I'll see you then.